All right, I think we're good. All right, so we're going to test claims about a population mean in practice, which means we do not know sigma. Sigma is not known. So in the last section, we knew what sigma was and everything was fine, but in this section, we don't. Okay, we tested claims about populations where we assumed the standard deviation was known. Now we're going to look at the procedure when we don't know it. So look at the two formulas. On the left, you have Z when sigma is known. And on the right, you have T and sigma is not known. Notice the difference. When sigma is not known, we use the student T distribution with n-1 degrees of freedom. So remember your book? The back flap inside your textbook is the student T distribution table. The back flap inside your book is the student T distribution. Okay, and it reads a little bit differently than what the Z table reads. Okay, anybody need anything here before I move on? JT, did you have a question or you just have your hand raised still? It's okay. All right, so just very quickly, you don't have to write all this down, just follow along as I go through it again. I'm just reviewing what the student T distribution looks like. First of all, it's different for different degrees of freedom. It's centered around 0 and symmetric about 0. The area under the curve is 1. As T increases or decreases without bound, the graph approaches but never equals 0. The area in the tails of the T distribution is a little greater than the area in the tails of a standard normal distribution because using S as an estimate of sigma introduces more variability to the T statistic. So these values are going to be just a little bit more than if we looked at the same value on the T table. Just a little bit more. As the sample size n increases, the density of the T gets closer to the standard normal density curve. This result occurs because as the sample size n increases, the values of S get so close to the values of sigma by the law of large numbers. So here's that law of large numbers coming back at us again. Now, what is this all saying? It's simply saying we have a whole bunch of these T curves. They look an awful lot like our Z curve. A whole lot of them. We have one for every degree of freedom. So we're always going to use n-1. And don't totally freak out on me. I'm going to show you how to do it the classical way, and I'm going to teach you how to do it on your calculator all in one lesson. And then you will choose what makes the most sense to you. I don't care at this point which one you use as long as you use one of them. All right, here we go. So, testing a claim regarding a population mean with sigma unknown, very much like what we just did. Claim is made. The claim is used to determine the null and alternative hypothesis. 2, select a level of significance, alpha, depending on the seriousness of making a type 1 error. 3, instead of computing Z, we're going to compute T with n-1 degrees of freedom. We use table 5 to determine the critical value, that's the inside cover of your book, with n-1 degrees of freedom. We compare the critical value to the test statistic. We state the conclusion. The only differences are this is T instead of Z. We use table 5 instead of table 4. Everything else is the same process. Okay, again, I'll give you a minute here to catch up with me, but this is exactly the same process we did, the same as the classical approach. This is the classical approach for a T distribution. This is the classical approach for the T distribution. Okay, let me know when you're ready to move on. I'm seeing thumbs. There's another one, another one. Good. Okay, almost there. Got it? Okay, looks like almost. Okay, I think we got it. Okay, you ready? Here it goes. So we have our test. It says to test H sub O, mu equals 100 versus H sub 1, mu is not equal to 100, a simple random sample of size 23 is obtained from a population that is known to be normally distributed. Again, why do we have to know this? Why do we have to know this? Because our sample size is less than the magic number of 30, right. Okay, so if X bar is 104.8 and S is 9.2, compute T. Formula for T. X bar minus mu. So 104.8 minus 100 over S, 9.2 over the square root of 23. Please calculate. I have 2.502. Yes, no? Okay, I'm seeing some head shaking. All right. If the researcher decides to test the hypothesis that the alpha is 0.01 level of significance, determine the critical values. Okay, now wait a minute. What kind of test is this? Left-tailed, right-tailed, or two-tailed? Left, right, or two? It is a two-tailed test. Good. Two tails, which means 0.01 has to be divided in half. So it's 0.005. We grab our book. We open to the back cover. We go down the left side to 22, because 23 minus 1 is 22. We go across to 0.005. Our answer is going to be plus or minus 2.819, I believe is what I read. Okay, agree with that? Okay, now that I have 2.819, I make my comparison. Well, let's take a look. Remember, we have a curve. We have negative 2.819. We have 0 in the middle. We have positive 2.819. Where does 2.502 land? Does it land in the safe zone? Or does it land in a tail? Well, 2.5 is smaller, so it's going to be over here, right? It's in the safe zone. So do we reject the null hypothesis? No. We fail to reject. Okay, classical approach. Same as we did in the last section, we just turned it into a T from a Z. So far, so good. Would you like to do another classical approach? You're going, not really. Can we do it with the calculator? Yes, we can. You ready? Okay, it's the same stuff. Okay, so according to the Centers for Disease Control, the mean number of cigarettes smoked per day by individuals who are daily smokers is 18.1. Mu 18.1. Yuck. A researcher claims that retired adults smoke less than the general population for daily smokers. Claim. Mu less than 18.1. You following me so far? Okay. To test this claim, she obtains a random sample of 40, N is 40, retired adults who are current smokers and records the number of cigarettes smoked on a randomly selected day. The data result in a sample mean of X bar 16.8, and a standard deviation S 4.7. Is there sufficient evidence at the alpha is 0.1 level of significance to support the claim that the retired adults who are daily smokers smoke less than the general population of daily smokers? All right, grab your calculator. We're going to do, I'm going to slide this over just a smidge. Hold on. Okay. Stat. Tests. Notice right under the t-test, or under the z-test is a t-test, so number 2. Enter. We're going to do it from stats. So we go down to the first one. The mu is 18.1. X bar is 16.8. S is 4.7. N is 40. And this is a left-tailed test. We go down to calculate. We hit enter. It tells me that T is negative 1.75, basically, and that P is 0.044. Okay, we're comparing P with 0.1. Is 0.044 more or less than 0.1?
Less.
It's less than 0.1. Therefore, we would reject H sub O. What would our conclusion be? Go back to your conclusion page. Does the claim have equal in it? No. So we go down. Do we reject? Yes. So what are we saying? I'm going to state it that way, creative license. There is sufficient evidence to support the claim that retirees smoke less. How we doing? Make sense? Again, we're comparing 0.044 and 0.1. This is less than. That is why we reject. Shall we do that again? Practice again? I think it's a plan. Anybody still need this one? Okay, in a study published by the American Journal of Psychiatry, researchers wanted to measure the effect of alcohol on the development of the hippocampal region in adolescence. The hippocampal region is the portion of the brain responsible for long-term memory storage. Researchers randomly selected 12 adolescents with alcohol use disorders. They wanted to test the claim that the hippocampal volumes in the alcoholic adolescents were less than normal. So, claim. The mean is less than 9.02. An analysis of the sample data revealed a hippocampal volume of approximately normal with X bar 8.1, S is 0.7. Do we have everything we need? I believe we do. So we go to, and then we have to look at our alpha. Okay, is this a one-tailed or a two-tailed test? Left-tailed, right-tailed, or two? It's a 1. Left or right? Left is pointing left, so we're going to go left. Yep. Okay, left. So this is a left-tailed test. I agree with you. We go back to stat. We go to test, we go to t-test, and we input our data. Mean, 9.02, X bar 8.1, 0.7, N is 12. It is left-tailed as we see, left-tailed, and we calculate. I have a p-value of 4.13. Wow, that's really, really, really big. I'm going to double check.
Times 10 to the negative fourth.
Yeah, see, I didn't read all the way across, did I? Yeah, I didn't read all the way across. Oops, calculate. Yeah, mine doesn't say that. Now it says my p is different. That's interesting. What did I do? Oh, I think I made it a two-tail. No? 8.1. Oh, my standard deviation is 0. Should be 0.7. There we go. Calculate. Yep, all the way over here, see the negative 4? So that means 1, 2, 3, 4, so 0.0004. So how does 0.0004 compare to 0.01? Well, I hope you all realize that is way less than. So what do? We reject. I cannot spell. Which means what? Same thing I did a second ago. We rejected, which meant we had sufficient evidence to support the claim that the hippocampal region is smaller. Yeah. Makes sense. Cool beans? Okay, you try. Oh, this one has data. So let's try one with data. Fun size of a Snickers bar is supposed to weigh 20 grams. Because the punishment for selling candy bars that weigh less than 20 grams is so severe, the manufacturer calibrates the machine so that the mean weight is 20.1 grams. The quality control engineer at M&M Mars, the company that manufactures Snickers bars, is concerned that the candy does not weigh 20.1. She obtains a random sample of 11 candy bars, weighs them, and obtains the data in the table below. Test the claim that the Snickers do not obtain the weight, Snickers do not have a mean weight of 20.1. Claim. Mu not equal to 20.1. It says does not weigh, so it must be not equal to. Because shutting down the claim is very expensive, she decides to test the claim that the alpha is 0.01. So alpha is 0.01. All right, so we go to stat. We're going to put our data in. So we're going to go to tests. Oh, nope, I'm sorry. Let's go back to stat and go to edit. And I'm going to use list 3. You can use whatever list you want. I'm going to use list 3. And I'll remember to change that when I get there. So 19.68, 19.98, 20.55, 21.5, 20.66, 0.65, 20.36, 19.74, 19.56, 19.61, and 21.02. I should have 11. I do. It says she did 11 candy bars, so N is 11. Okay, once I have my data in, I go back to test. So stat, test. I want the t-test, and I want data this time. Okay, and I know some things. It says I want it to be 20.1, so 20.1. I'm using list 3. I don't know what list you're using. My frequency is still 1. And I know that I want it to be two-tailed because it's not equal to. So two tails. So highlight two tails and calculate. All right, I have a p-value of 0.322. I want to compare this to this. I don't see anything else going on here, do you? So what should I do? Should I reject or fail to reject?
Fail to reject.
Why? Because 0.322
Bigger than,
is greater than 0.01. What does that mean? Okay, so let's walk through it. Does the claim have equal? No. I go down. Do I reject? No. What does that mean? Look at your sheet. What does it mean?
There is not enough evidence to support the claim.
Correct. IENT. That the mean weight is not 20.1. Okay? That's how it works. We've done without data, we've done it now with data. What do you think? Cool beans? Or not so cool? I see Emma going, not bad, not bad. Okay? Okay, I have one more, but I wasn't going to do it unless you wanted to do one more. Do you want to do one more, just practice? Most people are going no. Okay, then let me tell you that the homework assignment is page 538 to 540. It's numbers 6, 8, 10, 12, 15, 16, 18, 20, 22, and 23. I do not care if you use classical or if you use p-value. It makes no difference to me. These are the problems I'm asking you to do. I do want to double check one thing before I turn you loose. 20 to 23.
what's the last number?
23. Let me move it over. Sorry. Yep, there you go. Yep. Okay, so the last three, nope, 22 and 23 are data driven. All the rest of them are just questions in the book. I mean, just straightforward like we did at the beginning. Okay, so they're the last two, these two have data involved. All the rest of these are from stats. These two have data. Okay. Okay, I have a due date of this of 4/17. That would be Friday. Okay. Anything that comes in after midnight on Friday will be considered late, just so you know. And it shows up in my book as late, so it's not a big deal. I'm just letting you know. We have to keep this as normal as we can, and I need to continue covering material. Okay, I'm going to stop the video.